All right, let's look at another trig substitution example. And notice this time the squared variable is in front of the minus sign, followed by a number. So that's going to look like this. So that means this is going to be our substitution. Now, notice this is 1x squared minus a squared. So we do need to deal with that. We have to manipulate it just like we did with the formulas from the tables. So we're going to do a little manipulation here to make the formula work, and that's going to be to factor out this 49. And when I do that, I'm going to get an x squared minus 81 over 49 in the denominator. All right, notice the square root of 49 is 7, so this will come out as 1/7 the integral of dx over the radical, the square root of x squared minus 81/49. All right, now what is a square? What is it I'm squaring here? Well, notice it's perfect squares, so 9/7 squared is 81/49. So that is my value for a. So I would say that x is equal to 81/49 times the secant of theta. All right, and again, I'm going to show you both methods, but the first method would be to start off with the standard substitution. Or that should be 9/7. So 9/7 secant theta is what's being squared now, minus 81/49. Okay, if that's x, then dx is equal to 9/7, we'll just keep the constant. The derivative of secant is secant tangent, and that's what we're going to use to replace the numerator, d theta. All right, so there's my substitution. All right, now in my denominator, I'm going to take this 9/7, I'm going to square it. All right, that's going to give me 81/49, and that's underneath the radical. I'm factoring it out because that 81/49 is going to show up in both terms now. And when I factor it out, I'm going to have a secant squared theta minus 1. Right, when you do trig substitution, you're almost always going to need to have these little Pythagorean identities nearby because they typically show up. Notice this one right here. I've got a tangent squared and a secant squared, and I have underneath the radical secant squared minus 1. Well, if I subtract 1 over, I end up with secant squared minus 1 is tangent squared. So this underneath the radical is just tangent squared. Right, 81/49 reduces to that same 9/7 we see in the numerator, and then the square root of tangent squared is just the absolute value of tangent. But again, they tell us that even though this is a indefinite interval, they tell us that x is greater than 9/7. If x is greater than 9/7, then this secant function right here is an acute angle. Or we can treat it like this acute angle. It's an angle between 0 and pi/2, and so that means that this tangent is positive in that interval. All right, notice the tangent cancels here, the 9/7 cancels, and we're left with 1/7 the integral of the secant function. All right, I wouldn't expect you to know the secant function's integral off the top of your head, so it would be fine to go to chapter contents in my math lab, and there's the brief table of integrals. All right, and there we see on number 95, there's the secant function. All right, we can see a is just 1 here. So this is 1/1, 1, 1, all that is. So this is just 1/7 the natural log of the absolute value of the secant theta plus tangent theta plus c. Now remember, this is dx. The integral isn't with respect to x. We need to be able to get back to x. So we're going to need to take this substitution that we did, and even though this was the substitution method, I'm going to show you the trig method in a second, but even though this is the substitution method, we are still going to need to do some trigonometry here at the end when our integral is in respect to the angle and our differential in the original problem is x. We have to do some trig to kind of get back to it. All right, so I'm going to isolate secant here. And to do that, I'm going to have to multiply by the reciprocal here. So 7/9. And whatever I do to the left to keep it equal, I'm going to do to the right. All that's gone. And we're left with, I'm going to put the x up top. 7x over 9 is equal to the secant function. All right. Remember, secant is hypotenuse over adjacent. It's the reciprocal of cosine. So it's hypotenuse over adjacent. So I'm going to draw a right angle, put the angle right there, and the hypotenuse of that, which is opposite the 90 degree, is 7x. And the adjacent side, which is the side that forms the angle with the hypotenuse, is 9. And the Pythagorean theorem would then say that this is the square of the hypotenuse minus the square of the adjacent. Now, secant, we already know what secant is. But the other thing that shows up in this expression that we have down at the bottom is tangent. All right, so I moved our triangle down here so I don't have to keep going back and forth. But again, secant, that was hypotenuse over adjacent. So that was 7x over 9 plus, now tangent. Tangent is opposite over adjacent. So that's going to be the square root of 49x squared minus 81 over 9c. All right, you can leave it like that. You can combine them if you want to. Either way is fine. So either one of those expressions would be fine. That just combines into a single fraction inside. You cannot, however, hopefully you know this, but you cannot take the square root of those two things that are being separated underneath the radical by a minus sign. You cannot take the square root of each of these things and simplify that. That is absolutely not true, so make sure you don't do stuff like that. That's a way to lose all your credit on a problem by not knowing basic rules of algebra. So make sure you don't do something like that. Okay, but simplify these by their trigonometric definitions. You do need to get back to x. So make sure that you have that ability to create the right triangle and get yourself back to the original variable. Now, what if I wanted to do this entire problem but without the substitution, but the trig setup? Since you're going to have to do trig at the end. That's why I, personally, when I do trig substitution problems, I just go ahead and do the trigonometry to do the substitution. Because you oftentimes have to do trigonometry at the back end to get back to the original variable. So I just go ahead and do trig. But let me show you what this would look like. So it would be the same setup. We would do secant here because the squared x is in front. So everything that we did to begin would have been the same, meaning that I would have set it up the exact same to come up with the substitution. So x is going to be whatever's being squared here, and we can see it's 9/7. So 9/7 secant theta. And then I would set up my right triangle. Now, we'd already set that up in the last problem, but it would have been set up the exact same way. You isolate secant. I get 7x over 9. That means the hypotenuse is 7x. The adjacent side is 9. The opposite side is 49x squared minus 81. Okay? And when you set these up correctly, when you've done your trig correctly, that radical with the squared variable plus or minus, the other number, it'll show up if you've done your setup correctly. All right, now it's down in the denominator, and I don't have an x up here. Okay, so I'm not going to use this side. I'm going to use the 9 because there's no variable. If there had been a variable up top, if this had been x dx or like 5x dx, then I would have used the one that has the x. But since it's just dx, I don't want any x's. I want to use the number. So I need to create a fraction that has a 9 in the numerator and that square root of 49x squared minus 81 in the denominator. So I have to ask myself, what trig function of this angle would create that? And you can see this is adjacent in the numerator and opposite in the denominator. So that's cotangent. All right, I don't have a 9 in the numerator. I have 1, so I would say that this is 1/9 cotangent is what would put a 1 there. So now that you can see it, all of that, not the dx, let me take that dx away, that is just 1/9 cotangent. So that's going to be part of my substitution. The other part of my substitution is what I accidentally filled in before, the dx. So this is x, so dx is equal to 9/7. The derivative of secant is secant tangent d theta. So that is what I'm going to replace the dx with. All right, so I'm going back to the original integral. I did this to kind of set up what the substitution is going to be, but now I'm making my trig substitution on the original integrand. All right, so I got the integral of the 1 over the square root of 49x squared minus 81. All of that is just 1/9 cotangent theta. All right, and then the dx is 9/7 secant tangent. All right, and what's going to happen? Cotangent and tangent are reciprocals. The 9 will cancel away with 1/7 secant theta d theta. All right, and if you look, that is exactly what we ended up with right here after we made that substitution, simplified, used that Pythagorean identity and everything. We ended up with that. So from there on, the work's going to be identical. Every bit of it's going to be identical. It's just arriving at that trigonometric integral is completely different. You're not substituting in into an algebraic manipulation. You're literally taking the substitution you would make and creating a trigonometric definition of this relationship and using trigonometry to do the substitution. Either way is going to work. Either way, you saw that both paths lead us to the secant function, so both paths are going to get you to this integral. It's just that the reason I like this is because now when I do the integral and I get that secant plus tangent that's going to come out of the integration, the right triangle is already built. I don't have to do it again. It's already there, and I can just go right back in and plug in what the value of the tangent is. Okay, so that's the reason why I personally go with the trigonometric approach to set up these trig subproblems.